Okay, so here is part 6 of our video series where we're going through and trying to get through this practice exam. And so among a dozen eggs, 3 are rotten. Cookie recipe calls for 2 eggs. They'll be selected randomly from that dozen. Which plan can be used to simulate the number of rotten eggs that might be chosen? Well, the idea here is you have 12 eggs, right? So if you start with 0, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So I need to simulate the eggs, all right, with the appropriate number of values, right? So I need 12 values to simulate the eggs, all right? Then it tells me that 3 are rotten, so this is a characteristic of the eggs. So what I'm going to do then is assign maybe 0, 1, and 2 to be the rotten eggs. They're going to have that characteristic, okay? So here are my rotten eggs, and then here, all right, are my good eggs. And this is why I need to simulate each one of the eggs, all right? And now I'm going to choose 2, right? Because the recipe calls for 2 eggs. So now I need to draw 2 eggs, all right? And so my simulation needs to pull 2 numbers at a time. Now let's look. Number 1 says, hey, look, let's use 0, 1, and 2 to represent the rotten eggs, and 3 through 11 the good eggs. And then generate 2 random numbers, ignoring repeats. Okay, look, you can only pick an egg once. I mean, you have to actually break 2 different eggs, so that's why we're ignoring repeats, right? So you actually need 2 different eggs. Now there's another problem that's similar to this later on in the exam, where it has sometimes when you're ignoring repeats and sometimes when you're not. And so it's a big deal here that we're ignoring repeats. And so 1 is the correct answer. All right. Now, if you're going to randomly generate a 0, 1, or 2 to represent the number of rotten eggs, this is really bad for a great number of reasons. But the real reason is, okay, is that if you have just 0, 1, or 2, then the probability of getting a 0 is 0.3, the probability of getting a 1 is 0.3, and the probability of getting a 2 is 0.3. And that's not how they're divided up. It's 1/4 and 3/4. So 2 is not going to work because it doesn't preserve the proportions. And then since 25% of the eggs are rotten, let 0 equal rotten and 1, 2, and 3 equal good. Well, this is not a good way of doing it, because it isn't either just rotten and just good. You're picking 2 different eggs. So you need to draw twice. Well, this one's only drawing once, okay? It is true that 25% of the eggs are rotten, but that doesn't mean that 25% of the samples are going to be rotten. And so this is just an oversimplification that's going to lead to some bias, because you're trying to pick 2 different eggs, and so that means you need to draw twice, and here I'm only drawing once. So 3 is going to be bad. So 1 only is C, and so that makes us happy. So now let's look at 26. Okay, so hoping to get information that would allow them to negotiate new rates with their advertisers. Okay, Natural Health Magazine phoned and had a random sample of 600 subscribers. Okay, so this is going to give us our N and our population. Okay, 64% of those polled, there's your P, said that they use nutritional supplements. Was actually P hat, right? That they use nutritional supplements. So this is my characteristic, right? So use nutritional supplements is my characteristic, which is true. The population of interest is the people who read this magazine. Yeah, because we're looking at subscribers. I told you that was the population. Okay, so this is true. 64% is not a statistic, it's a parameter of interest. Well, this is false, okay? It is a statistic because it's created from a sample. A parameter comes from a population, okay? So this one's false. This sampling design should provide the company with reasonably accurate estimate of the percentage of all subscribers who use supplements. Yes, and this comes straight from the central limit theorem, that if I have a large enough sample, right, and I do meet the 4 assumptions, then my sample should be near the actual proportion of the population. And so this is good. And so 6 is going to be 1 and 3, which is B. Okay, and so B is going to go right here. All right, so just 1 and 3 only. Okay, now we have a very similar type question in 27. Okay, so the January 2005 Gallup Poll had a random sample of U.S. teens. Okay, so the U.S. teens is going to be our population, and ask these teens to name their favorite movie from 2004. So we're looking at favorite movie from 2004, okay? And then we have 8% of teens ranking it, okay? So this sort of gives us our whole idea here. The 8% is going to be our p hat, 0.08, right? Of teens, that's our population. So the population is teens, right? And the characteristic that we're looking at is a ranking of the movies, okay? And so the population of interest is all U.S. teens. Yes, check. 8% is a statistic, not the actual percentage. That's correct, right? It's from the survey, so it's a statistic, not a parameter. And this sampling design should provide a reasonably accurate estimate of the actual percentages. Well, this means that our assumptions have to be met so that we can use the central limit theorem. And remember, our assumptions are independence. Yes, if you're phoning them randomly, it's probably independent. 2, it's got to be random. Okay, random is actually in the sentence there. 3 is it's got to be less than 10% of the population. I am guessing that there are more than 10,000 teens in the United States. And then 4, you have to have at least 10 successes and 10 failures. Well, 8% of 1,000 is about 100, so you have at least 100 successes and 900 failures, and so this is going to be met. So that means the central limit theorem says that my p hat is going to be close to my p. And so this is going to be a fairly good one. And so this is all 3 of them are met, and so we have E. Okay? And now I'd just like to do 28 to finish up the video. All right? Okay, and so suppose your local school district decides to randomly test high school students for attention deficit disorder, right? ADD. Okay? There are 3 high schools in the district, each with grades 9 through 12. The school board polls all of the students together and randomly samples 250 students. Is this a simple random sample? Well, yes, this is definitely a simple random sample. They had 3 high schools. They pooled them all together, and then they took their sample. So this meets the requirement because everybody, yes, all right, because they could have chosen any 250 students from throughout the district. So the answer here is A. Now, how come it's not B? All right, yes, because each student, here's a yes, right? Because each student is equally likely to be chosen. Well, you can get that from a cluster sample, right? Every student is equally likely to be chosen from a cluster, or a stratified, which are 2 other methods that we talked about, okay? And then no's not right because it is, and no's not right because it is. And then yes, because the students were chosen at random, okay? Well, there's also randomness in all of the other types of cluster, right? And stratified, and even systematic, right? And so the one that really separates each of these is not because they were equally likely to be chosen, right? In a cluster and a stratified, you have that. Not because they were chosen at random, cluster, stratified, systematic, those all have that too. But because any of the 250 students from throughout the district could have been chosen. So it's going to be A here, all right? And that concludes this video. We're going to do 29 in part 7. I hope you'll continue to watch.